My name is Dan Oake and I'm a student at Athabasca University, currently taking the course Computer Science 444, Embedded/Robotic Programming. If you followed my previous video, I went through the SparkFun Inventors kit and showed how to do Circuit 1A of Project 1. It was quite a long video, over an hour, and basically went through the start of the SparkFun Inventors kit and talked through Circuit 1A in rather lengthy detail, going through the code. And so I'm going to continue off from there, hopefully go a little quicker, and just show circuits 1B, 1C, and 1D. So we were on page 20, where I just went through the code to note section of Circuit 1A, and then I talked about the coding challenges and started to talk about the troubleshooting. Basically, if your code wasn't uploading, make sure you've selected your board. If it's still not uploading, make sure you have the correct port selected, and make sure your LED is in the right way, because LED is a polarized component. And last but not least, it could be your jumper wires that just aren't working, so replace those. So what my code looked like previously, I showed the coding challenge for the Morse code coding challenge. So it looked something like this. If I plug this in, this is the simplified version of the coding challenge for Circuit 1A, where it's Morse code blinking LED with no LCD. And so basically I had a Morse code dictionary set up, which, if you're not familiar with Morse code, you would just go to Wikipedia, type in Morse code, and it'll tell you these symbols associated with the 26 letters of the alphabet. And then in setup, I set up pin 13 as an output pin, because that's the pin that is going to have the LED attached to it. And in the loop, I basically check to see if there's anything available via the serial monitor. And the reason I'm checking for that is because I'm going to use the serial monitor to type a message to be sent out via Morse code, meaning to be interpreted via Morse code for the LED. Basically, if there is a message, I read that message until the end of the sentence, till the next line, when enter was pressed. I make sure there's no white space associated with the message, and then I just go through the string, the text message that was sent in the sentence, character by character, and convert each character to Morse code. And I've got some helper methods to do that. Blink Morse code that takes in the character and either calls the blink dot or blink dash method, depending on what needs to happen based on the letter. And these are the two methods that do that. Blink dot and blink dash essentially turn an LED on and off with a certain amount of delay, depending if it's a if it's a dot versus a dash. The delay for a dash will be 3 times as long, and that's according to Wikipedia. So that's the code that's currently loaded up on there, I believe. So I'll just type in hello world and see. So if I type in hello, in fact we'll just start with hello, you'll see that light blink 4 times, indicating H, and then once for E, and once, then a dash, and 2 for L, and then again another 1 and a dash, and 2 dots for another L, and finally 3 dashes for O. That was the simple version, so you can see the code for that is coding challenge is that long. I also had a more complicated version, which showed take that down, don't save. I had a more complicated version that had LCD involved, so I'm just going to upload that. So the more complicated version, I have the LCD involved, and I went through that in detail last time, but essentially it's the same thing. It just displays the message on LCD. So if I was to type in hello, sending hello dot dot, 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 that's H, single dot for E, and then dot, dash, dot, dot for L, and then do that again for another L, and then end with 3 dashes for an O. And then I had just display in scrolling text hello with the corresponding alphabet letters and the symbols. So that was coding challenge 1. And obviously you could enter something else. Bye. But that was coding challenge 1, and now we're going to move on. So that was a quick recap of what we've already done. Now I'm going to go on to coding challenge 2. Okay, so now that we've completed circuit 1A, which was have that LED blink, circuit 1B deals with a potentiometer. So potentiometers, also known as trim pots or knobs, because it's a knob that you turn, are one of the basic inputs for electronic devices. Basically, by tracking the position of the knob with your breadboard or any Arduino compatible microcontroller, or any microcontroller for that matter, you can make volume controls, speed controls, angle sensors, and lots of other useful things as input for your projects. So we're going to use it to control the speed that the LED blinks at, i.e. the amount of delay we put in our code. So for this circuit, we're going to need an LED, a potentiometer, which is our variable resistor, a 330 ohm resistor, and 7 jumper wires. So the new components we're going to talk about this time are a potentiometer, which again is just a 3-pin variable resistor. The middle pin outputs a voltage between 0 volts and 5 volts. That's what gives us our variable resistor. The position of the other 2 pins, by the way, are just going to be hooked up to 5 volts and ground. It doesn't really matter which one you hook up to 5 volts and ground. It'll just make the behavior a little backwards, but it doesn't really matter. One of them needs to be hooked up to ground, one needs to be hooked up to 5 volts, and then the middle pin, known as the wiper, needs to be hooked up to your input, analog input. So, again, the position of the knob is going to give you 0 to 5 volts. There's an internal trim pot. Internal to the trim pot, or the potentiometer, whatever you want to call it, is a single resistor and a wiper, which cuts the resistor in two when you move it, and it adjusts the ratio between the two halves. So again, if it's a 10 kilo ohm resistor, it means if from one pin on the left edge to the pin on the right edge, there's 10 kilo ohms of resistance possible. You can either use all 10 kilo ohms of resistance if you have the knob turned all the way to one side, or 0 resistance if you have it turned the other way, or anywhere in between. But again, it's basically a single resistor is inside the potentiometer, and a wiper basically adjusts the ratio of what part of the resistance you're using. Some of the new concepts we're going to talk about are analog versus digital. So analog is the world we live in, so where there's an infinite number of inputs. So you think of the temperature. The temperature isn't just 22 degrees and then instantly 23 degrees and then instantly 24 degrees. No, it can be 22 degrees and then 22.1 degrees, 22.2 degrees. Or instead of being 22.1 degrees, it could be 22.001 degrees. And again, an infinite number of possibilities in between. So that's what analog means. So we live in an analog world where there's an infinite number of signals or an infinite number of possibilities. Discrete signals, on the other hand, have a discrete or finite values. So they're a limited set of values. So in the LED's case, and in our digital circuits, we have 2 values. We accept only states of on or off, true or false, high and low. So again, for the LED, it's either on or off. Analog inputs, just like we had our 14 digital inputs on this side, we have 6 analog inputs on this side. And again, analog inputs are used to sense a wide range of values versus digital input, which would only sense two values, on or off. So we'd use digital inputs for things like push button, where the button is either pushed or not pushed. Whereas analog inputs are usually hooked up to sensors like temperature sensors or things of the like, or a potentiometer that can read a wide range of values. Digital and you can either have pins that are digital or analog in. And there's a reason they're called analog in, is because they're set up to be inputs only. So there's only 6 pins for analog inputs, whereas there was 14 digital pins. And again, the function of the analog pins is as inputs. And they're labeled as A0 through A5 for analog 0 to analog 5. Voltage divider. We're also going to talk about voltage dividers. So that's a new concept for us. And voltage dividers are just simple circuits that turn some voltage into a smaller voltage using 2 resistors. A potentiometer is a variable resistor that can be used to create an adjustable voltage divider. But again, the main thing associated with a voltage divider is you're taking some voltage, so some input voltage, say 5 volts from the microcontroller, the breadboard, and you're turning it into a smaller voltage by use of 2 resistors. And in our case, we're going to use one of the resistors is going to be a potentiometer, which is a variable resistor, so that we can create an adjustable voltage divider. Whereas if you use 2 just resistors, you're going to create a voltage divider, but it's always going to be the same voltage that you get out. So the smaller voltage is always going to be a set value. Whereas with a potentiometer, we can create an adjustable voltage divider. So the schematic for this hookup is we're still going to have the LED hooked up as we did in circuit 1A, where the negative leg, the shorter leg, and the flat edge on the LED is hooked into ground. In this case, we don't hook it directly into the circuit board as we did in the first circuit, but instead we're using the negative or ground rail associated with the breadboard, and then that rail is attached to ground. So now this whole rail here is all negative. And then we've also got our positive 5 volts from our microcontroller hooked into the positive rail of the breadboard. So basically anything we hook into here is essentially like it's being hooked to the 5 volts of the Arduino, or the breadboard rather, and anything hooked into the negative rail is essentially connected to ground of the microcontroller. So the LED is connected just as it is before, but instead of connecting it directly to the breadboard, we're connecting into the negative rail, and we're connecting the positive leg of the LED through our 330 ohm resistor and into digital pin 13 just as before. And again, I mentioned this in the last video, but this resistor could be, as long as it's in the circuit somewhere with the LED, it's fine. So in this case, it's in the positive leg. It could have also been between ground and the negative leg, and then the positive leg could have been hooked in directly to pin 13. It's as long as the LED is in the circuit somewhere. Finally, for our new component, we have one of the exterior pins of the potentiometer hooked into the negative rail of the breadboard, which is ultimately connected to the ground pin of the breadboard of the breadboard, the microcontroller, and then the other terminal, the other exterior terminal of the potentiometer, connected to the positive rail, which again is ultimately connected to the 5 volts of the microcontroller. And then the middle pin, which is known as the wiper, is connected to analog input 0. So again, that's the main one. And again, your negative and positive connections here could be reversed. It will just reverse the behavior of the potentiometer, the way what is the 0 range and what is the 5 volt range, but it would be fine. But it's the middle pin that is needs to be hooked up into analog 0. Again, you're just going to go to your examples and load the code that you got off the SparkFun Inventors Kit website. So again, you're going to want to load the example for circuit 1B. You're going to select upload and just upload that to your program. And this is kind of what the circuit looks like there. Mine is a little more jumbled up, a lot more stuff on there, which I'll talk about in a second. So again, the program overview is simply we're going to read the position of the potentiometer, which is going to be from 0 to 1023. That's the values, the possible values on the potentiometer. That's what the analog input reads. because it has a 10-bit resolution. So, and because it's binary, 2 to the 10 is 1024 different values, and that's from 0 to 1023. We're going to read the position of the potentiometer and store it in a variable called pot position. We're then going to turn on the LED, and then we're going to wait from 0 to 1023 milliseconds, whatever value we read in based on the pot. And so based on that position, we're going of the knob and the value of pot position, we're going to wait that amount of time. So we're going to delay the program that amount of time, and then turn off the LED, wait that same amount of time that we read from the pot position, and repeat. So basically it's still just a blinking LED program. It's just this time, instead of turning the LED on for 2 seconds or 2000 milliseconds and then turning it off for 2 seconds, we're turning it on and then turning it on for an amount of time based on what we read in from the pot value, and then turning it off for that amount of time. So our blink delay is going to be controlled by our pot, our potentiometer position. So that's what that's, and then this is the code to note, but first let's go to the code. So this is still my old Morse code pattern. So the new code is, this is circuit 1A. Actually, that's my code challenge, so I will instead pull up, this is the example guides I think I showed previously. Let me just do this again. I think I showed previously where to find the examples associated with the SparkFun guide. So in the Arduino IDE folder, there's an examples folder which has all the examples that come with Arduino, plus the ones I put in there from the SparkFun Inventors kit guide. So this is the potentiometer example. Let's just pull that up. Okay, so now we're just going to go through the code in detail. So again, as always, these SparkFun examples start off with a multi-line comment using the /* and ending with an */, and they basically just explain what the code does. So in this case, changes how fast an LED connected to pin 13 blinks based on the potentiometer connected to pin A0. And then it has links to see the circuit diagram and instructions, as well as you can download this code. So basically, what does the code do? Well, we create a variable for the pot position, and it's in variable of type int, and this variable will hold a value based on the position of the potentiometer. And then in setup, we simply call the serial.begin method with passing in 9600 as the baud rate. That's just so we can start serial communication with the computer. We use the pin mode function to set up pin 13 as an output, because that's the pin that has our LED on it, and we want to set it up as an output so that we can, call the digital write function and set it high or low, i.e. turning the LED on or off. This code will run exactly once, because that's what setup does. It only runs once, and then the loop code runs over and over for the entire life of the program. So first of all, we're going to read the position of the pot, the potentiometer, by calling the analogRead method and passing in A0, which just tells it I want to do an analog read off of this pin, A0, which is our analog read, and we're going to assign that value to pot position, which is just our int variable that we created up here that's going to store the position of the potentiometer. And then we're just going to print whatever that value is to the serial monitor so we know what position it's at. And then we're just going to change the LED blink speed based on that pot value. So we're going to call the digital write method, calling digital write on pin 13, and we're going to set it high. So we're going to turn pin 13 on, i.e. turning the LED on that's connected to pin 13, and we're going to have it turned on for the amount of time that we read from the pot position. So we're going to call the delay method, passing in pot position as the value, which is an int variable that will change depending on the position of the potentiometer. Then we're going to turn the LED off by calling digital write again and passing in low as the second argument, and we're going to delay for the same amount of time. So again, our blink delay, the amount of time between our LED being on and off, is is going to be decided by the position of the potentiometer. Also note, you might notice that I only call pin mode once, setting pin 13 as an output pin, and pin 13 is of course again the pin that our LED is attached to. But I don't call it twice. You're probably wondering why I don't call pin mode with pin A0 and call it input, because as discussed, we have pin A0 as an input because that's what we're reading for the potentiometer off of. However, we don't have to do this because the analog pins are all input pins, so they don't do output, they only do input. So by default, because they are only input pins, we don't have to call pin mode on them and set them as inputs. They are in fact just input by default. So that's that. Now we can use them as digital pins, so we could use them as an output pin in digital pins, but by default they are meant for input pins, so we don't have to call the pin mode function on them if we're using them as intended, which we are in this case. So as you can see, this code simply reads in the position of the potentiometer and then turns on an LED for that amount of time. So let's upload this code. Let me see here. So we're going to upload this code to our Arduino, port 16, board, it's an Uno. So as you can see, the LED is blinking at a certain rate, and we'll open up the serial monitor to see what that rate is. So what's being output to the serial monitor is the position of the LED. It's at currently 1017, and remember, the values that we can read in on the analog pins are they have 10-bit resolution, which is 2 to the 10th power, which is 1024, meaning there's 1024 possible values of resolution, which goes from 0 to 1023. And so because we're reading right now 1018, we're essentially all the way at one end. So I'll take an Allen key. This type of potentiometer has an Allen key in it, and I'm going to turn it all the way to the end, and you can see that, yeah, it's still reading 1023 or 1018, so 1021, there you go, 1023. So it's all the way at the end, so it's all the way turned in one direction, so we're getting the full value, and that's why we have such a long delay between the LED, because it's based off of 1023 milliseconds, because that value 1023 is being passed into the delay function, which expects an int representing the number of milliseconds to delay for. So that's just over a second delay, whereas if I turn it, you'll notice in the serial monitor that the value goes down. If I can actually get this in there, you'll notice the value goes down. So right now I'm at 836, and you can see the blink is faster because I'm still over half a second, but it is a faster delay. If I make it go down really low to 246, so now the potentiometer is down to a value of around 250, which is, a quarter of a second. You can see the blink has increased a lot. And then if I put it all the way down to 0, it doesn't even show 0 at this point. You can see the LED is blinking, but it's going so fast, it's not even really showing up in the camera. Yeah, it's going so fast you're not really able to see that it's shutting off. So I'll make it a little slower. So now we're at about 80 milliseconds. So still fairly low, and you can see that it's blinking incredibly quick. And again, you'll see the onboard LED of the Arduino here flashing at the same rate, because again, digital pin 13 is hooked up to that onboard LED, so that'll blink at the same rate as this one. That's only for digital pin 13. But anyway, I'm going to lower this speed So I'm going to put it back up. I'll put it about halfway at around 5:08, and you can see it's about a half a second blink. So that's just the regular Circuit 1A code that comes with that you can just download from SparkFun. So that's just the regular thing, just using a potentiometer to control the blink speed of the LED. However, when we go to the there's also a coding challenge, which I'm going to talk about in a minute. But first, let's go to the code to note. So what was the code that we've seen here? Well, we're dealing with integer variables now. So in particular, we have a variable that's a placeholder for values, and it may change, hence the name variable. It varies. And variable names are case sensitive, so be careful with that. And the first variable we created, again, was pot position, and it was a variable to store the position of the potentiometer. And we did that by having the potentiometer on analog A0. And again, the middle pin of the potentiometer outputs a voltage between 0 and 5 volts depending on the position of the potentiometer. So we read that in, and then we interpret that as such, a value between 0 and 1023, and we use that number that we read in to control the amount of time we delayed the program, and therefore the blink delay. We also use serial communication this time. So we use serial.begin and passed in an argument of 9600, which is basically the baud rate that we want to communicate serially. So basically how fast we want the serial communication. 9600 is a fairly common one, but there's different values. Another common one we'll end up using when speed's a little more important is 115,200, but 9600 will work for most of our stuff. Again, serial commands basically send and receive data from the computer. And the baud rate needs to be the same on the monitor as well as in your code. So for example, in the code, if I say 9600 as a baud rate, and you can see everything is working good here down in the serial monitor, we're getting good values. But if I was to change the baud rate in the serial monitor to something like, say, 115,000, you'll see we don't get readable values. We get this garbage value because the baud rate that we're saying that the serial monitor should be in the code doesn't match what our serial monitor is. So if we want to get readable data and values, we have to make sure that the baud rates match. So the speed of the two devices communicate at must be the same. And then we talked about analog input, basically where we did you called the function analogRead, which took only a single argument in, whatever pin we want to read from, which is one of the analog pins, and we read that value in. That'll give us a value between 0 and 1023, and we assign that to our pot position variable, which is a variable of type int. So again, analogRead just reads a value from an analog pin, and it only takes one parameter argument rather, and returns a number between 0 and 1023. 0 corresponding to 0 volts and 1023 responding to 5 volts, because again, the analog pins are reading input in the form of the reading voltage, and it's up to us to interpret that and do it something meaningful with it. Then finally, we use the serial communication to print things to the serial monitor. So we did serial.println and printed just the value of that we were reading from the potentiometer to the screen. Again, the main thing we were using it for was to control the speed at which the LED blinks, but we also wanted to see it for our own values. And then this is what we actually want to get looking at today, is the coding challenges. So we're going to what this coding challenge was, it says changing the range. So try multiplying, dividing, or adding to your sensor reading so that you can change the range of the delay in your code. For example, you can multiply the sensor reading so that the delay goes from 0 to 2046 instead of 10 to 23. So in this case, the sensor is referring to our potentiometer, and right now we're just reading it as is, and when we read it on an analog pin, again, we can only read, it'll give us a value between 0 and 1023. But we want to increase the range to be from 0 to 2046. So we're going to need to multiply our range and do some math there in order to extend that range. Also, we're going to add more LEDs, so adding more LEDs to your circuit. Don't forget the current limiting resistor. So again, with every LED, you should have a current limiting resistor. Because again, LEDs are sensitive devices, and we don't want just to give as much current as the microcontroller will give to the LED, because it will likely damage the LED and cause it to blow up. And by blow up, I mean just get really bright and then not bright ever again. But we don't want to do that. So you will need to declare the new pins in your code and set them all to output. So just like we called pin mode on pin 13 and set that as an output pin, we'll do that for any additional pins that have LEDs attached to them. Try making individual LEDs blink at different rates by changing the range of each using multiplication or division. So that's all that we're going to do in this code today. So this is the simple code where we just, from the challenge, where we originally, before the challenge, where we just did an analog read on pin A0 that had the wiper or a potentiometer attached to it, and then we turned on, we called a digital write to pin 13, turned it high, so turned the LED on, and delayed for that amount of time that we read in, and then shut it off. And now we're going to do, don't save, our coding challenge. So I've already written the code for the coding challenge the other day. Actually, let's put it over here. So, nope, that's not the coding challenge. It keeps opening up the original file for some reason, so I'm going to do it this way. Okay, so now it looks like we have the right file, so let's just look at this. So again, as before, I'm just going to go through the code. So basically, I just built on top of the previous code, so that's hence why I still have the same comment here. But really, I should probably take this comment out and explain. You would want to explain, use this code to explain what this circuit is actually doing, which is, has multiple LEDs and working a little different than the original one. I also have some LED code in here that is doing, that is not necessary again for the coding challenge. I've just added an LED for my own purposes. I'll explain it once with the LED, and then we'll take that out to declutter things. But because the LED is here, we'll talk about this first. So this line of code is just including the liquid crystal library, which is the library associated with the LED. So we've just included that. As well as these two constants are also associated with the LED. And this number 6 here, I'll just lower the font so you can get more of the comment in there. So hashtag define LCD contrast pin, number 6. That is, again, just the contrast pin. That's the pin that's attached to, that affects how the backlight and the text show up. So basically, what you find is a good level so that you can see the text properly against the backdrop. There's no text on the screen now in case you're wondering if you don't see anything. But that is pin number 6. I've just made it a constant. So that way, in case I change that, because sometimes if I have a different LCD, different Arduino board, it might be in a different spot. So I can change it in one location. I also have created a constant for the contrast level that I'm going to set to the pin. So again, you typically would hook it up, the LCD, to a potentiometer and adjust it manually. But I'm using a technique where I'm using software to adjust it. Again, I can send in a value between 0 and 255, and I've just got a value set roughly in the middle at 127, and this value will be used to set the LCD contrast level between 0 and 255, or 0 volts and 5 volts, but using software as opposed to an actual potentiometer. And then this code here just initializes the library, the instance of the liquid crystal object from the library, with the numbers of the interface pins. So again, in the previous examples, I actually declared constants, either defines or constants, for these values. But in this case, I just put in the magic numbers of the values directly, I think for simplicity. But basically, the first argument is the value associated with the register select pin. The next one is with the enable pin. And then the last 4 pins are for the data transfer pins, D4, D0, D1, D2, and D3 pins. So we only need 4 pins for transfer. There's technically 8 data pins on the LCD, but we only need 4 of them for our purposes. But this is just creating an instance of the LCD so we can use it. And then I have a function here called init LCD, which is basically just, it does a lot of the initialization, the things you need to do to use the LCD. And you could normally just call all of this code directly in the setup function, which is what I've done other times. But just using, anyone who's familiar with programming and why we use functions, it's just to abstract away code and kind of make our code more modular and readable. So I've just abstracted away some of the LCD code that's, again, just used to initialize the LCD in the first place and would normally be called in the setup. I've just put it all in this one function, so when I call it in setup, it's just one function call, and it abstracts away all this detail. But basically what I'm doing is, first I'm calling the LCD.begin function that takes in 2 arguments representing the number of columns and number of rows, and this is a 16 column by 2 row LCD. This is fairly standard LCD. Then I call the pin mode function, setting up the LCD contrast pin, which is pin number 6, as an output pin. Again, I'm going to set up a microcontroller pulse width modulation pin as an output pin, and again, that's to control the contrast, basically how well you see the text on the LCD. And then I'm going to call the analogRead function, passing in 2 arguments. One, the pin that I want to write information to, which is my LCD contrast pin, pin number 6, and then the level that I want to write to it. Again, I can send in a value I could just put an int here from 0 to 255. I've created a constant up here that represents 127 because once I set this, I don't really need to change it. And again, analog write is it's similar to digital write, but whereas digital write can only write values, it can either write high or low to a digital pin, basically sending 5 volts to a digital pin or 0 volts, 5 if it's high, 0 if it's low. Analog write will allow you to send anywhere from 0 to 255, a value from 0 to 255, representing from 0 volts to 5 volts. But it can only be called on certain pins. And ironically, you can't call this on an analog pin. This can only be called on digital pins that are special digital pins that are known as PWM pins, or pulse width modulation pins, which are, I'll use the red board here, which are special digital pins that have this little tilde symbol beside it. So digital pin 3, 5, 6, as well as 9, 10, 11, all are pulse width modulation pins. And they have this just little weird tilde symbol beside them to indicate that they're pulse width modulation. And they're able to, instead of just being written high or low, meaning having 0 volts sent to them or 5 volts, they can have, again, any values between 0 and 5 volts within the resolution of 0 to 255. And the reason I would do that is so that I can send a different value. I'm not just setting it high or low, but in this case I'm setting it somewhere in the middle to receive about 2.5 volts, which just is the amount that I think looks good for seeing the text on the backdrop of the LCD. And then this is fairly standard stuff. Whenever you're going to print something to the LCD, you call the setCursor method, pass in two parameters. The first one represents the column number, second one represents the row. So 0, 0 represents the first column, because remember, as computer scientist, we count from 0, not 1. So the first column and the first row. So it's going to be right here where the text starts. And then we're simply going to print lcd.print code challenge 2, where we're printing a message to the LCD. And again, that's 16 characters long. Remember, you can only print up to 16 characters because, well, that's all that all the columns you have in this little LCD screen. And then we're going to print lcd.print pot varies blink. Just what I've called this. Again, I didn't have to set the cursor again. Theoretically, I could have called lcd.setCursor and passed in 0 and 1, indicating the first column, but the first row, like so this row here, the bottom row. But I didn't need to because of the fact that this string was exactly 16 characters. So the cursor just automatically would move to the 0, 1 position, so the 0 column, first row, and print. But if this wasn't quite 16 characters long, say it's 15 characters, I would have to call the setCursor method again. Otherwise, I'm going to start printing right after the spot here, and my P is going to be somewhere here. So in this particular case, I didn't have to call it, just because this code worked out to be exactly 16 characters long. And then I delay for 2 seconds just so that the user can read this little message I'm printing out, and then I call the lcd.clearScreen method. So that's all just happening in setup. So I just encapsulated it in one function, called it init LCD, which I call in the setup function. So in setup here, I call init LCD, which just initializes the LCD for use in the project. I also have this other function I've created called print to LCD that takes in a single parameter called of type int, named value, and still doesn't return anything. And basically, it's just what I'm going to use. Whatever I pass to that, I'm going to print to the LCD. So the LCD screen by itself has a function just called print that you just pass things in it. But I'm calling this because I'm doing a few things, and I want to encapsulate that in a function. So again, I'm calling the setCursor method, setting at 0, 0, so this upper left corner. I'm then printing to the screen LED blink delay, and again, this happens to be exactly 16 characters, I believe. 4, 9, 10, 11, 12, 13, 14, 15, 16, yeah. So I don't actually need to call this setCursor method again, where I'm setting it up as column 0, row 1, right here on the bottom row. But, I do to be explicit, and that's fine. Sometimes, like here, I wasn't explicit, here I am. Just kind of sometimes do this kind of inconsistent thing just to show how different things work. Kind of like I've done here. I've used two different ways of defining a constant. They both result in calling a constant. You typically wouldn't have defines and then call constants this way because they're contradicting. Well, they're not contradicting, they're just two different ways to do the same thing, and it's just not consistent. But a lot of times I do that just to show different methods, because you'll see different methods in tutorials. So anyway, sidetracking again. So I set the cursor to the bottom row, and then I print a value. What's the value? Well, whatever I pass into this function, which we'll see later. And then I just print a bunch of empty space, basically filling up the rest of the bottom line. It's just a technique that's better than calling the lcd.clear method, which just has some issues and it flashes, doesn't look as good. So those are two user-defined methods I've created. I put them above here. I could have also put them below the code and had setup and loop appear earlier in this program like normal, but I basically just wanted to show you that all this code between these two commented lines that say LCD code are all associated with the LCD. That's why I kept it there. So we'll be able to take that code out later when I show you a simple version without the LCD. Then finally, again, this is what we typically see when we come to a program. After we've included any libraries that we need, we typically do any constants values that we want. In this case, I'm using hashtag define to define blue LED as a name representing pin 5. So that's where my blue LED is connected to. And then I'm using this newer sort of syntax for declaring a constant by just creating a variable as usual. So, a variable called green LED of type int, and I assign the value 4 to it using the assignment operator and semicolon. And then I just put the keyword constant in front of everything, just indicating it's a constant. And that's for green LED. Again, I could have done defines for both or constants for both. I actually prefer define, although this is kind of an older style that's kind of legacy from C, because Arduino is based on C and C++, and in C we did more defines, whereas in modern C++ you typically do constant. But with defines, the convention is to make everything uppercase, the names uppercase, and words separated by underscores, and you don't use an assignment operator or semicolon. You just do it the way you see it here. Whereas with the newer method, you just have a variable name as usual, an assignment operator, and assign some value to it, and you use the keyword const in front of essentially just a regular variable statement, but it makes it a constant. Some people still follow the convention where you make the name of a constant all uppercase and individual words separated with underscores, but a lot of times you don't see it that way. So I've just shown it in the way that you don't see it, like a variable. I actually prefer to still make all my constants as uppercase letters, so I would still prefer this, just because when I see that in the code later, I know that that's a constant and not just some variable that I can change. But I kind of try to show both ways, so that way you can kind of see what's going on. And then I've actually created a bunch of variables, so not constants, but a bunch of variables that will change. The values will change. So pot position, this variable will hold a value based on the position of the potentiometer. Adjust delay, this variable will store the adjusted delay value. So that's kind of like the first code. The pot position then affected the delay of the blink. I've just named it adjust delay here before, where I just used pot position directly in a delay function. And then I've got two more adjusted delays, adjusted delay 2 and adjusted delay 3. And really, they're all doing the same thing. It's just I have 3 separate LEDs I'm using. So, and you'll notice I've only created 2 constants. One for blue LED, one for green LED. But I've also got a red LED here. However, I just used the same code as before. I've used the magic number 13 in here. Again, not good code. If I was actually making this code, these would have all been either defines or constants, and I would have the red LED up here as well. So I would have done hashtag define, red LED, and had pin 13, and used that name down here, and it would have been very clear. Oh look, I'm setting up a red LED, a blue LED, and a green LED all as outputs. But again, I'm just trying to show you all kinds of different things in one piece of code. And then, so yeah, those are the constants and variables I've created. And then now we just get to setup. In setup, we're doing the same thing we did before. We call the serial.begin method. We set up the serial monitor with 9600 baud rate. So that's just starting the serial connection with the computer. I call the pin mode function on all 3 of pin 13 and pin, 5 and 4 that have blue LED and green LED attached to it. I set up all the pins that have my LEDs on them as outputs. And then I call the init LCD function. That was the user-defined function I created that basically sets up my LCD screen. And then in the loop, first of all, I'm going to read the position of the potentiometer, same as I did in the non-code challenge, by calling analogRead on pin A0. And that's going to return a value between 0 and 1023, based on how far the knob is turned. And let me just make this a little bigger for that purpose so we can see the full comments. I'll move this over if you want to see that. It's not really important right now, but so, and then what I'm doing is I'm gonna go serial.print. I'm gonna print to the serial monitor, which again will print here. I'm gonna print to the serial monitor. Something saying I'm going to print the string raw pot value, and then I'm going to print the pot position, which is the value I read in from analogRead. So that's just going to print off a value between 0 and 1023 to the serial monitor. And then I'm going to adjust the range by multiplying the potentiometer value, so as per the coding challenge. So I'm going to take the pot position, the value I read, which is between 0 and 1023, and I'm going to times it by 2. So multiplying by 2 to scale the range from 0 to 1023 to 0 to 2046. However, it will be in even number increments only. So I'm not actually scaling the range fully to get full resolution between 0 and 2046. No, I'm really still getting almost the same range in the sense it's 1,024 different values. I'm just skipping all odd numbers. So it's really going to be, I'm going to be able to have a value of 0 and 2 and 4 and 6 and so forth, all even values. But and assign that to adjusted values. So just I've created a new variable that was declared above, and I assign pop position times 2 to that value. And then I basically just print that to the serial monitor as well. And I do the same thing for adjusted value 2 and 3, but this time I take the pop position value and divide it by 2. So now instead of having a value from 0 to 1023, I'll have a range of half that. And then I'm going to finally, for the last one, I have pop position times 1. So I guess I'm just, for the last one, I decided to just basically have the same pop position. Times something by 1 essentially doesn't do anything to it, so I'm still going to have a range of 0 to 1023. But I can change that after, and we'll do something different with it. And then basically I just change, as before, I just change the LED blink speed based on pop value. This time I just have 3 different LEDs. So the first one is kind of the same as it was in the previous example. I turn digital pin 13 high for a certain amount of time based on the adjusted delay, which in this case is from 0 to 246 now. So basically, instead of a possible 1 second delay, anything from 0 to 1 second delay, now I have a delay from 0 to just over 2 seconds, possibly, based on the pop position, and then I turn it off for that same amount of time. So again, the red LED, because this is hooked up to the red LED, pin 13, will now have a possible delay of 0, meaning it won't be delayed at all and just constantly be on, to a value just over 2 seconds. And then I do the same thing for the other 2 LEDs. So blink or toggle on and off the blue LED with the delay based on the multiple of the pot value read in on the microcontroller analog pin. So, and again, I'm just going to print that value. I'm going to call the print LCD function I created, passing in adjusted delay 2. And that just means I'm going to print on my LCD screen whatever the blink rate is for that blue LED. And then I'm going to call the digital write function again on blue LED, turning it high for the delay according to whatever this variable got stored in it, based on some multiple of the pot value. And then I turn the LED off for that same time. And then I do the same thing for the green LED. I blink it at a certain speed based on the pot value, some multiple of the pot value. So with all that said, let's upload the code and see if that works. So pin 16, uno, let's do that. So I'll restart this. I'm not sure if you can tell on the screen. Again, it's hard to see. Code challenge 2. Yeah, it's probably really hard to see. So before I get too involved here, let's just change the contrast level that we have and see if we can make this better. Okay, so that's a little better at 100. So again, I just changed the contrast level. Again, I could have done this directly with a potentiometer, but I'm just doing it in software. I'm just going to reset the LED so we can start from right from the start. So it says code challenge 2, LED blink delay, and it shows the different LED blink delays, which are 1026, 256, and 512. So what does that mean? Well, let's take a look over here. The first blink delay we know is, and the same thing is being mirrored on the serial monitor here. So the first blink delay is actually just the raw pot value. So right now, 1026, that just means the potentiometer is all the way one way. And then second blink delay, as we know from the code, let's look at the code. The second blink delay is based on the adjusted value is we adjusted the scale from 0 to 246. So we have a value from 0 to 246, which is going to be possibly from 0 to 2 seconds. And then finally, we do a blink delay of, correction, where am I here? We half the pot position, and we'll have a value of half that. So that half value, if it's at 1024, 1023, half would be about 512. So that's kind of what we're seeing here. We're seeing the 1024, the full value. Then we're seeing 256. That seems a little off to me. That should be times 2. So let's just see what's happening there. 256 when we know that should be times 2. Let's see. The raw pot value is 512. Oh, the raw pot value's correction is 512. My bad. So I guess the potentiometer is actually set to half. So that's the raw pot value. So that's the first adjusted delay, which isn't really adjusted. The second value, which is times 2, is the 1024. And then the fourth value is just the fourth value would be half of the pot value, which would be 256. So again, I'm going to stop this scrolling for a second so I can unconfuse myself. So if we follow here on the screen, the raw pot value is 512, which is the potentiometer set at about halfway, because again it's got a range of 0 to 1024 when being read in an analog pin. So halfway is 512. The adjusted value is 1024. Why is that the case? Well, because the adjusted value, the adjusted delay, is based on the pot value times 2. Well, 512 times 2 is 1024. And then adjusted delay 2, I guess I've named these weirdly. This should have been adjusted delay 1. But adjusted delay 2 is the pot value divided by 2. Well, if the original pot value was 512, divided by 2 is 256. And then finally, adjusted delay 3 is back to 512. So it's the exact same as the raw pot value because I just have it times by 1 here. So that's what's happening. And the blinks are following that. So the red LED blink delay is, red LED is 1036. The blue LED is at, happened really quick, but it's at a 2 something. And the green LED is at 518. So again, the raw pot value is coming in. We're doing an adjusted delay. The first one, which is based with the red LED, is times 2, which means it's at 1036. The next one is half of the original, which is at 2 something. And then finally, we're back to the original value, which the pot is halfway, so it's 518. Let's adjust this to full value, which is what I thought it was, which was why I was so confused with the math. So right now, I've got it all the way, so the original pot value now is all the way to one end, meaning the blink delay on red, which is times 2 of the original value, is now almost 2 seconds, or just over 2 seconds. This one will be half of the original value, which will be about half a second. And then this one is at times 1, which is just the same as the regular value, which is 1. Let's adjust that third one instead of having it at 1 and have it at 0.75, just to get a little more dynamic. But this is essentially the code here. We'll clear this. So code challenge 2, LED blink delay. So right now the full value of the LED is about, it's all the way to one side, so 1024. Therefore, when we times that value by 2, which is what the red LED is based on, that's going to be over 2 seconds. The blue LED is going to be half of the original value, which is about 512, so half a second. And the green LED is about 0.75 of 1024, which will be around 750 or something. So, and those delays, so we're affecting the blink delay of the LED. So you can see each one blinks slightly differently. So that was coding challenge number 2. Again, you don't need the LED. This could have been a lot simpler by simply, I'm just going to file, save as no LED, or no LCD rather. Just take a second here. So I'm just going to take out all the unnecessary stuff, i.e. the comments at the top, and everything between this commented line here that says LCD code and this line here that's LCD code is not necessary for this coding challenge if you're not using the LCD. And I will leave the defines in here for now and the constant, just because otherwise I'll have to change them down here. And I'll leave these variable values as well. But at least by taking out the LCD code, it gets a little simpler. Not horribly, but a little bit. So now if we upload this, we'll see that we still have the same functionality. Just wait. Print to, okay, well I'm trying to print LCD, but I've taken away that code, so let's just get rid of those. Get rid of some of these comments just to shorten this code up. Okay, so now I think that's all of the LCD code gone. Let's see. And there's one more lingering there. Oh, print LCD right here. Let's hope we got it that time. So in the new code, we won't see any display on the LCD, but we should still see the same blink rate based on the potentiometer. So that's about 2 seconds after it loads up. Start the serial monitor, which actually restarts the code sometimes. As you can see there, it restarted the code. So again, about a 2-second blink on the red LED, shorter blink, like a half of that on the blue, and then a 3/4 on the green. So you can see the same code is still happening. The same blink, the pot is still affecting the blink rate of the lights. We just don't have any LCD display, so it just makes it a little simpler. And again, if I lower that quite a bit, we'll see the blink rate get faster for all of them. If I lower that again. So I've made it a lot quicker. There still is a difference in the blink rate, as you can see over here. If I stop this for a second. The pot value is 50. The adjusted delay, which is 2 times the pot value, is at 100. Half of the original pot value, which is 50, is now 25. And then 3/4 is at 37. So they're still at a different blink rate. They're just harder to tell because it's so quick. And again, up the pot value a little bit more to 234, and again the values are still displayed. But anyway, that's for coding. That's for circuit 1B and coding challenging associated with that. And we'll end this video here, which is again very long, and I apologize. And we'll come back with coding for circuit 1C and 1D, as well as the challenges associated with it. And I will try to be quicker. I really got to figure this out.